Welcome to the first lecture in this machine learning course. This lecture series is based on the book Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow by Aurélien Géron. I strongly recommend reading the book alongside this course. The link to purchase it is in the description. Today's lecture covers the machine learning landscape. We'll define what machine learning is, explain how it differs from traditional programming, outline key terminology, types of learning systems, and real-world applications. Let's get started. Let's start with a question. What powers tools like optical character recognition, email spam filters, and digital assistants like Siri? You might assume it's just clever programming, but the real answer is machine learning. Machine learning, often abbreviated as ML, refers to the process by which computers learn to perform tasks using data instead of being explicitly programmed with rules. This means that instead of writing a massive rulebook, we allow the computer to extract patterns and relationships from data. This adaptive behavior is what powers many intelligent systems we use every day. From personal assistants to image recognition, machine learning is behind the scenes making sense of the world in ways that are often invisible to us, but deeply impactful. So what exactly is machine learning? In its simplest terms, machine learning is the science of programming computers to learn from data. That's an important distinction. Machine learning is not about feeding computers more information or facts. Instead, it's about enabling them to improve their performance at a specific task based on experience, where that experience is provided in the form of data. To understand what this means in practice, consider the problem of email spam. Every day, people receive unwanted or malicious emails spam, which can be annoying at best and dangerous at worst. A basic spam filter needs to automatically detect and separate these spam messages from legitimate ones. With traditional programming, we'd write a list of rules. If an email contains certain keywords like win money or click here, mark it as spam. But this approach is limited. Spammers constantly change their language to avoid detection, using tricks like spelling words differently or embedding text in images. As a result, rule-based systems quickly become outdated and require constant manual updates. The spam filter begins by analyzing the contents of each email, looking at the words, structure, sender information, and other characteristics, and converting that information into a form the model can process mathematically. It then uses this data to learn which patterns tend to appear in spam versus legitimate emails. For example, it might learn that certain phrases, email formats, or combinations of features are common in spam messages. Over time, and with enough examples, the filter becomes capable of recognizing spam even when the exact wording changes. It doesn't rely on a fixed set of rules. Instead, it adapts by learning from data. This ability to generalize from past examples to new, unseen messages is a core strength of machine learning. Let's take a moment to check your understanding before we move on. Here's your first quiz question. Which of the following best describes what machine learning really is? 1. Writing fixed rules to solve problems. 2. Programming computers with facts. 3. Learning patterns from data to improve performance. 4. Feeding the computer more RAM. Take a second to pause the video and type your answer in the comments. Don't overthink it. Just your best guess. The correct answer is 3. Machine learning is all about using data to help a system recognize patterns and improve its performance on a task over time without explicitly writing out every rule. It's very different from traditional programming. Now let's go over some essential machine learning terminology. First, a dataset is a structured collection of related data, often formatted as rows and columns. It serves as the foundation for training and evaluating a machine learning system. From this dataset, we typically define a training set, which is the portion used during the learning phase. Each row in the training set is called a training example, a single instance from which the system learns. In many ML systems, learning happens through a model, which is a mathematical or algorithmic structure that captures patterns in the data. The model is adjusted during training, so it can make predictions or decisions. However, not all systems build explicit models. Some, like instance-based learning algorithms, store training examples and make predictions by comparing new data directly to stored examples. When a system, whether model-based or instance-based, is used to make predictions on new, unseen data, This process is called inference. Before we dive deeper, let's make sure the core terms are sticking. Here's your next question. What do we call a single labeled example used in training a machine learning system? 1. Test instance. 2. Inference sample. 3. Training example. 4. Output feature. Pause the video and comment your answer below. These kinds of details really matter, especially when we start writing code or reading papers. The correct answer is 3, a training example. That's one row or instance from the training set. It's what the model uses to learn patterns from the input features and target label. Why use machine learning at all? The main reason is that many tasks involve complexity that makes them hard or impossible to solve with rule-based programming. For example, it's nearly impossible to write down all the rules for recognizing spoken language or detecting fraudulent behavior on a credit card. Machine learning shines in scenarios where rules change frequently or are difficult to define in advance. A great example is a spam filter. Instead of constantly updating a manual list of rules, a machine learning model can continually adapt to new patterns of spam as they emerge. Moreover, machine learning is invaluable for discovering patterns in large datasets. This process, often called data mining, helps uncover insights that might otherwise remain hidden. Let's now look at some real-world applications of machine learning. In healthcare, machine learning models are used to detect tumors in medical scans with increasing accuracy. In finance, ML systems detect fraudulent transactions in real time by analyzing patterns in user behavior. Recommendation systems, like those on Netflix, YouTube, or Amazon, use machine learning to suggest content based on your preferences. And in the domains of voice and image recognition, ML enables software to understand and interpret human speech and visual data more accurately than ever before. Machine learning systems can be categorized in 3 main ways. First, we can look at training supervision, whether the system learns from labeled or unlabeled data. Second, we can consider whether the system learns incrementally or in one big batch. And finally, we can ask whether the system generalizes by comparing examples or by building a predictive model. These 3 dimensions help us distinguish between different types of ML systems, and each has strengths suited to different types of tasks. The first major way to categorize machine learning systems is by their level of supervision during training. This refers to whether or not the training data includes labels, that is, the correct answers the system is supposed to learn to predict. In supervised learning, each training example comes with both an input and a corresponding output label. The goal is to learn a mapping from inputs to outputs, so that the system can make accurate predictions on new, unseen data. Take spam classification as an example. Each email in the training set is labeled either spam or not spam. The input to the model is the content and metadata of the email, things like the subject line, sender address, and message body. The model learns from these labeled examples to predict whether a new email should be classified as spam. Another example is housing price prediction, where the input features might include square footage, number of bedrooms, and location, and the output label is the house's sale price. Given enough examples, the model learns how changes in input features affect the output and can then estimate prices for new properties. In unsupervised learning, the data has no labels. The system isn't told what the correct answers are. Instead, it must identify patterns, structure, or relationships in the data on its own. A common example is customer segmentation. Suppose you have customer data, age, purchase history, website behavior, but no labels saying what kind of customer each one is. An unsupervised algorithm like k-means clustering can group customers into segments based on similar behaviors, even though you never told it what types of customers exist. Another example is dimensionality reduction, where the goal is to compress high-dimensional data into fewer dimensions while preserving important structure. This can be useful for visualization or improving the performance of other algorithms. Anomaly detection is another key unsupervised task, for instance, detecting fraudulent credit card transactions by identifying purchases that don't match a user's typical spending behavior. All right, let's try another one. Think about the difference between supervised and unsupervised learning as you answer this next question. You're given a dataset of customer behavior, but it has no labels. You want to group similar customers together. What type of learning should you use? 1. Supervised learning. 2. Reinforcement learning. 3. Semi-supervised learning. 4. Unsupervised learning. Pause here, choose your answer, and drop it in the comments below. The right answer is 4. In unsupervised learning, we don't have labels, so the algorithm has to find patterns or clusters all on its own, like in customer segmentation. In addition to supervised and unsupervised learning, there are a few more specialized learning paradigms that fall somewhere in between or operate under different assumptions. Semi-supervised learning is used when we have a small amount of labeled data and a large amount of unlabeled data. This is common in situations where labeling is expensive or time-consuming. For example, imagine a photo app that wants to organize your images by person. You might label a few photos with names, say, "This is Alex," and "This is Jordan," but you don't label the hundreds of other pictures on your phone. A semi-supervised algorithm can use the small labeled set to learn a rough idea of what Alex and Jordan look like, and then apply that knowledge to cluster or identify the unlabeled photos. It effectively bridges the gap between supervised precision and the abundance of unlabeled data in the real world. Self-supervised learning takes a different approach. It generates labels from the data itself without requiring human annotation. This is common in natural language processing. Take the example of training a language model. We can feed in a sentence like "the cat sat on the" and ask the model to predict the missing word. The sentence provides both the input and the label. The masked word becomes the prediction target. This kind of pretext task allows the model to learn language structure, grammar, semantics, context, without needing external labels. A similar approach is used in computer vision, where models are trained to predict the position of missing parts of an image or to reorder shuffled image patches. Once pre-trained, these models can be fine-tuned on smaller labeled datasets for downstream tasks like sentiment analysis or image classification. Reinforcement learning is fundamentally different. Here, an agent learns by interacting with an environment, not from labeled examples. The agent tries actions and receives feedback in the form of rewards or penalties. Over time, it learns a policy, which is a strategy for choosing actions that maximize cumulative reward. A classic example is training an AI to play a game like Go or chess. At first, the agent makes random moves, wins or loses, and receives feedback based on the game outcome. Through repeated trials, sometimes millions of games, it learns which sequences of moves are more likely to lead to a win. This trial and error process is how systems like AlphaGo mastered the game of Go and defeated world champions. Reinforcement learning is also used in robotics, autonomous driving, and recommendation systems where decision-making is sequential and feedback is delayed. This next question is about one of the newer and rapidly growing paradigms in ML. Which learning paradigm generates its own labels from unlabeled data? 1. Supervised learning. 2. Self-supervised learning. 3. Semi-supervised learning. 4. Reinforcement learning. Go ahead and pause to make your choice, and comment if you're following along. The correct answer is 2. Self-supervised learning. This is often used in NLP and computer vision. The system creates pseudo-labels from patterns in the data itself, like predicting the next word in a sentence or filling in missing parts of an image. Next, let's look at how machine learning systems learn over time. This brings us to two important paradigms: batch learning and online learning. In batch learning, the model is trained all at once using the full dataset. Imagine you're training a spam filter. You collect a large dataset of emails, say 100,000 examples, and you train your model on this entire set at once. Once training is complete, the model is frozen. It won't change unless you retrain it. If you later collect 10,000 new emails, you can't just add them to the model. You have to retrain the entire system from scratch using both the old and the new data. This is why batch learning is sometimes called offline learning. It's not continuously updating. This method is reliable and efficient when data doesn't change often. But it can become impractical when new data is constantly arriving or when retraining is too slow or too expensive. Now consider online learning. In this setup, the model updates itself incrementally as new data becomes available. Think of a news recommendation system. Every minute, users click on new articles, and the system wants to update its understanding of what's trending. Instead of waiting to retrain on a full dataset, the model ingests this new data on the fly, adjusting its parameters in real time. This makes online learning ideal for fast-moving environments like stock trading, personalized ads, fraud detection, or anything that requires continuous adaptation. A key concept in online learning is the learning rate. This determines how much the model adjusts in response to each new data point. If the learning rate is high, the model adapts quickly to recent data, which is useful in fast-changing environments, but it also runs the risk of overreacting to noise or outliers. If the learning rate is low, the model updates more slowly, which makes it more stable, but it may miss important short-term trends. Setting the learning rate correctly is crucial. Too high, and the model may become unstable. Too low, and it may become sluggish or unresponsive. In summary, batch learning is like printing a final version of a book you write, edit, then publish. Online learning is more like writing a blog that evolves every day based on reader feedback. Let's test how well you understood the difference between batch and online learning. Which of the following scenarios is best suited for online learning? 1. An annual population census. 2. Real-time stock trading predictions. 3. Housing price modeling from last year's data. 4. Sorting archived documents. Pause here and see if you can get it right. Add your answer in the comments. The best answer is 2. Online learning is designed for situations where new data is constantly coming in, and you need the system to adapt quickly, like in stock markets. Now let's consider another important distinction in how machine learning systems generalize from data. Instance-based learning versus model-based learning. In instance-based learning, the system doesn't try to build a general model or abstract rules. Instead, it memorizes the training data and uses it directly to make predictions. When the system sees a new input, it compares it to all the examples it has stored and tries to find the ones that are most similar. For example, imagine a medical diagnosis system that stores past patient records. When a new patient arrives, it searches for patients with similar symptoms and makes a prediction based on the outcomes of those similar cases. This process relies on a similarity function, such as Euclidean distance, which measures straight-line distance between points, or cosine similarity, which compares angles between feature vectors. A common algorithm that uses this approach is k-nearest neighbors. If you set k equal to 3, the system finds the 3 most similar stored cases to your input and then makes a prediction, like a diagnosis or a classification, based on the majority label among those neighbors. This method is simple and often effective, but it can be computationally expensive at prediction time and may not generalize well if the training data is noisy or high-dimensional. In model-based learning, the system tries to learn a general function that maps inputs to outputs. Instead of storing all the examples, it uses them to fit a model. This could be a mathematical equation, a decision tree, or a neural network. A classic example is linear regression. Suppose you're predicting house prices. You collect a dataset of homes with features like square footage, number of bedrooms, and location, along with their sale prices. The system fits a line, or in higher dimensions, a plane or hyperplane, that best predicts price from these features. Once trained, you can plug in the features of a new house, and the model outputs a predicted price. This is much faster than searching through past examples, and it allows you to generalize beyond the training data. However, model-based approaches often rely on assumptions. For instance, linear regression assumes a linear relationship between features and the output. If this assumption doesn't match the reality of the data, the model may underperform. In summary, instance-based learning makes predictions by comparing to past examples, while model-based learning builds an abstracted model that captures patterns across the data. Each approach has its strengths and weaknesses depending on the nature of the problem, the size of the data, and the computational constraints. Okay, quick knowledge check. This one's about how different machine learning systems generalize. Which algorithm is an example of instance-based learning? 1. Linear regression. 2. Decision trees. 3. K-nearest neighbors, or KNN. 4. Support vector machines. Take a moment to think it through, and as always, pause the video and drop your answer in the comments if you're following along. The correct answer is 3, k nearest neighbors. Unlike model-based approaches like linear regression or support vector machines, KNN doesn't build an abstract model during training. Instead, it memorizes the training data and makes predictions by comparing new inputs directly to stored examples using a similarity measure like Euclidean distance. It's simple and often surprisingly effective, but it can become slow as the dataset grows because it has to compute distances to every stored example. To train a model, we need a way to measure its performance. That's where utility functions and cost functions come in. A utility function tells us how good our predictions are. A cost function tells us how bad they are. During training, the goal is typically to minimize the cost function by adjusting the model's parameters. This process is known as optimization. By minimizing cost or maximizing utility, we improve the model's ability to make accurate predictions. Despite its power, machine learning isn't without challenges. One major issue is insufficient data. Complex models require lots of examples to learn effectively. If you don't have enough data, the model may underperform. Another problem is non-representative data. If your training data doesn't reflect the real-world environment where the model will be used, your results will suffer. This is often caused by sampling bias or noise. Poor quality data, data with errors, inconsistencies, or missing values can also degrade model performance. Data cleaning is essential before training. Lastly, using irrelevant features can cause your model to learn spurious patterns. This is where thoughtful feature engineering becomes vital. Two very common problems in machine learning are overfitting and underfitting. Both can seriously limit how well a model performs, especially when it is applied to new, unseen data. Let's start with overfitting. This happens when a model learns the training data too well, even memorizing specific examples instead of learning general patterns. Imagine you're teaching someone to identify birds, and you give them a training set of 100 photos of robins. If they memorize the exact details of those photos, like the background trees or the exact angle of the bird, they might do great on the training images. But when you show them a new robin photo taken in a different location or from a different angle, they get it wrong. That's overfitting. The model has latched onto noise or irrelevant details instead of learning the broader pattern of what makes a robin a robin. In machine learning, this leads to high accuracy on the training set, but poor performance on test data. On the other hand, underfitting occurs when the model is too simple to capture the patterns in the training data. It hasn't learned enough from the data to make useful predictions. Continuing the bird example, imagine you just tell someone, if the bird is small, it's a robin. That's too simplistic. It misses key features like the red chest or the shape of the wings. In machine learning, an underfit model might have low accuracy even on the training set because it can't represent the underlying patterns in the data. We address overfitting by simplifying the model, feeding it more training data, or using a technique called regularization, which penalizes overly complex models. To fix underfitting, we might use a more complex model that can learn richer patterns, or we might improve the quality of the input features by using better data or transforming existing features to make them more informative. The goal is to find the right balance, a model that is flexible enough to learn from the data, but not so complex that it learns the noise. Let's do one more check-in before we move on. A model performs really well on the training data, 98% accuracy, but only 60% on the test data. What's most likely the problem? 1. Underfitting. 2. Cross-validation error. 3. Generalization success. 4. Overfitting. Pause now and give it a shot. Type your answer in the comments if you're following along. The correct answer is 4. Overfitting. The model has memorized the training data instead of learning the general patterns. That's why it fails on new, unseen data. Feature engineering is the process of selecting and crafting the right inputs for your model. This includes selecting only the most relevant features, transforming features into more useful formats, or even creating new features by collecting additional data. Good feature engineering can often make a simple model outperform a more complex one with poor inputs. To evaluate how well a machine learning model will perform on new, unseen data, a concept known as generalization, we divide the available dataset into several distinct parts. Each part serves a specific role in the development and evaluation process. These parts typically include the training set, the validation set, the test set, and in some cases, a train dev set. The training set is the portion of data used to train the model. During this phase, the model learns by adjusting its internal parameters to reduce prediction error. For instance, in a spam detection system, the model is trained to recognize patterns that distinguish spam emails from legitimate ones using labeled examples in the training set. After training the model, we need to evaluate how well it will generalize to new data. For this, we use the test set, which is a completely separate portion of the dataset that remains untouched throughout the training and model selection process. The test set is used only once, after all design decisions and hyperparameter tuning are complete. The purpose of the test set is to provide an unbiased estimate of the model's generalization error, which reflects how well the model is likely to perform in real-world settings. However, we typically do not move directly from training to testing. Before reaching the test set, we use a validation set. The validation set is another reserved portion of the data used during development to tune the model's hyperparameters. Hyperparameters are configuration settings that are not directly learned from the data, such as the learning rate, the number of decision tree splits, or the number of hidden layers in a neural network. The model's performance on the validation set helps guide which combination of hyperparameters yields the best results without touching the test set. To further improve reliability and avoid overfitting to the validation set, we can use a method called cross-validation. In cross-validation, the dataset is split into several equal-sized parts, or folds. The model is trained on some of these folds and validated on the remaining ones. This process is repeated multiple times so that each fold is used as a validation set once. The results from all iterations are then averaged, giving a more stable and reliable estimate of model performance during tuning. Another important tool for diagnosing model performance during development is the train dev set. This is a small subset of the training data that is held out, not for tuning or final testing, but for checking how well the model generalizes within the training distribution. The train dev set shares the same data distribution as the training set, unlike the test set, which might reflect future or production data. If the model performs well on the training set, but poorly on the train dev set, it is likely overfitting. If the model performs poorly on both the training and train dev sets, it is likely underfitting. Using a train dev set allows developers to identify problems in model capacity or training behavior before moving to final evaluation while keeping the test set untouched and unbiased. In general, for small datasets, a common practice is to allocate 80% of the data to training and 20% to testing. In larger datasets, the test set might comprise just 1% of the data, or even a fixed number of examples, such as a few thousand, depending on the use case. Regardless of size, the key principle is to isolate the test set completely until the final model is ready to be evaluated. Each dataset partition plays a crucial role in the machine learning workflow. The training set is used to teach the model. The train dev set is used to check whether the model is overfitting or underfitting. The validation set is used to select and tune the model. The test set is used to evaluate how well the final model generalizes to unseen data. Let's see how well you remember the different dataset splits we talked about, especially the one that often gets overlooked. Here's the question. Which dataset split is used specifically to diagnose overfitting before we ever touch the test set? 1. Validation set. 2. Test set. 3. Train dev set. 4. Training set. Go ahead and pause the video here, think about it, and if you're following along, post your answer in the comments. The correct answer is 3, the train dev set. This is a small subset of the training data held out not for tuning or final testing, but to help us check whether the model is overfitting or underfitting, all within the same data distribution as the training set. If your model performs well on the training set but poorly on the train dev set, that's a sign of overfitting. If it performs poorly on both, you're likely underfitting. This diagnostic step is crucial before doing final evaluation on the test set, which should always remain untouched until the end. And now a humbling truth, the no free lunch theorem. It tells us that no single machine learning model works best for every problem. Just because a neural network works wonders in one domain doesn't mean it will outperform simpler models elsewhere. That's why experimentation and iteration are key. Try different models, understand your data, and tailor your approach to each specific problem. To wrap things up, machine learning enables us to build data-driven, adaptive systems. It learns from data rather than explicit rules, making it ideal for complex, dynamic problems. But building a good ML system takes more than just choosing an algorithm. You need to carefully prepare your data, select the right features, evaluate your models thoroughly, and stay aware of challenges like overfitting and data bias. Thanks for watching this lecture on the machine learning landscape. I hope it gave you a clear and practical introduction to how machine learning systems are built, trained, and evaluated. If you found this helpful, make sure to like the video and subscribe for more lectures in this series. And if you have any questions or want to dive deeper into a specific topic, feel free to leave a comment below. I'd love to hear from you. See you in the next lecture.